Okay, the notes for Chapter 3, Day 5 starts with a warm-up review question. The stuff on the right is from the previous day's lesson, but the stuff on the left says the function is defined for all real numbers and has the following property. Find f prime of 2. So if you look at that for a few minutes, you might be able to figure out how to find the derivative and then substitute -2. We'll go over this in class. So the first of two theorems that rely on continuous and differentiable intervals is called Rolle's theorem. Rolle's theorem says that if a function is continuous on a closed interval and then differentiable on an open interval, and if there are two y values that are the same, then there has to be at least one number such that the first derivative equals 0. In other words, there has to be a point where the slope of the tangent line is 0, or there has to be a horizontal tangent at some point. So the picture on the left is a demonstration of Rolle's theorem working. We have two y values are the same, the function is continuous and differentiable everywhere, so there has to be a point where there's a horizontal tangent or the first derivative equals 0. The second one fails because while we have two y values that are the same and while the function is continuous, the function is not differentiable everywhere. At that point there, the slope of the tangent lines from the left don't equal the slope of the tangent lines from the right. These two slopes look different. So since it's not differentiable there, Rolle's theorem does not apply. So the example for this, which is a calculator question, involves quite a messy rational function, but you can still walk through the steps without having to slog through pages of algebra. The first thing I want you to notice is that we have a rational function where the denominator is x to the fourth, so there's a vertical asymptote at x equals 0. In order to use Rolle's theorem, we must have continuous and differentiable on the interval we're looking at. So since the interval is -3 to 1, and since we have this vertical asymptote at x equals 0, so far we're okay. Vertical asymptote means that the function would not be continuous, but other branches of a rational function are continuous, except for where the vertical asymptotes occur. So we have a continuous function, and it is also differentiable. We could take the derivative of that and get this. We don't have to go through the whole thing. Remember, the derivative of a rational function is ho d high minus high d ho over ho squared. The only thing we're really concerned about is the denominator. The denominator, again, the only number that we can't use is 0. 0 is not inside the interval that we're looking at, -3 to -1, so it is differentiable everywhere, and the two conditions for Rolle's theorem are met. The third condition says our two y values the same. So we're going to take the two endpoints of the interval, -3 and -1, plug them into the function, and wind up with -1 and -1. So we know that Rolle's theorem can be applied, and now we need to find the location C where the horizontal asymptote exists. This is the difficult part. The first derivative is quite messy to figure out by hand, so we get to use our calculator, but Texas Instruments calculators can't really graph derivatives very easily, so I switched to Desmos. This is a smaller picture of what Desmos can do, and I'll show you a better screenshot of it in a second, but I want you to look at the function here in red, and it turns out that between the 2 points of -3 and -1 and -1, -1, there is a horizontal tangent at that point there, which when I use Desmos would be -0.312. And how did I get that? First I had Desmos, I typed the function in, had Desmos graph it, and if I click on the function, some important points get highlighted in gray, and when I click on that point there, it tells me that the maximum, the local maximum in that area is at -1.312 and -0.589. To verify that that's correct using the first derivative, I had Desmos graph the derivative, so I told it to take the derivative with respect to x of f of x, which is up here, plot it, and horizontal asymptotes have a first derivative equal to 0. So now when I look at the blue function and look at the x-intercept, the x-coordinate of the derivative is -1.3120, so that tells me that at the input of -1.312 is where the maximum occurs. Now this grayed out is different. That's the intersection of the two, the blue and the red line, but the maximum point, which is no longer highlighted on the red function, does occur with an input of -1.312, which is the C value we were looking for. So part B of this problem is a much smaller function, so it looks like it would be easier to do. Is it continuous? Yes. There are no domain restrictions on x to the 2/3 minus 1 between -8 and 8, so yes, it is continuous on the closed interval. Is it differentiable? Yes. When I take the derivative, I wind up with this 2/3 x to the -1/3, which moves the x into the denominator, but now the derivative does not exist when x equals 0. This function has a domain restriction because x is in the denominator. So since the derivative does not exist everywhere in the interval -8 to 8, that's one of the conditions for Rolle's theorem which fails, so Rolle's theorem cannot be applied to this function here in B. And finally, the second of the two theorems that we're looking at that use continuous and differentiable functions again says that if you have a continuous function on a closed interval, and if you have a differentiable function on an open interval, in other words, you don't need to worry about being differentiable at the endpoints of your interval, then there has to be a number c somewhere on that interval such that this statement is true. And what that statement is saying is that the left side, which is the instantaneous rate of change, has to equal the right side, which is the average rate of change somewhere on that interval. What does that mean? The instantaneous rate of change is the slope of the tangent line, and then the average rate of change is the slope that you get when you connect the 2 points of a secant line. So somewhere in the interval from A to B, if I connect the 2 points, I'll get a slope. There has to be a location somewhere that has an instantaneous rate of change or a derivative equal to that same exact slope. So walking through this example, we're given a function. Here it is. We're supposed to plot it by hand and find the point at which the mean value theorem is satisfied. So to plot this function, I'm going to take a cosine graph and move it up 2, but I'm only going to go from 0 to pi over 2. So a cosine graph that gets moved up 2 starts at 1, moving it up 2 puts it at 3. At pi over 2, you would have it at an x-intercept, so when you move it up 2 units, you're here. And there's your cosine plot between 0 and pi over 2. Is it continuous and differentiable? Yes, mostly by inspection, but we know we can take the derivative and it doesn't have any domain restrictions, and that function, trig functions are continuous over the interval. So the mean value theorem says the instantaneous rate of change has to equal the average rate of change at some point c. Can we take the derivative of that function? Yes, the derivative of 2 is nothing. The derivative of cosine is negative sine. Average rate of change, I'm going to use my 2 endpoints of pi over 2 and 0 for b and a, so I need pi over 2 plugged into the function, 0 plugged into the function, which reading it off the graph gives me 2 and 3. The right side simplifies down to -2 over pi. The left side, I'm looking for the location where the first derivative matches the average rate of change. So I have a c there and I need to solve for c. C equals the inverse sine of 2 over pi. That's your answer. So part B says plot the secant line and the tangent line, and it's a calculator question. So I put the original function into y1, and to get the tangent line, I'm going to use point slope form. The point that I need is c f of c. So c is the x-coordinate, and f of c is the y-coordinate, and here's c right here. And then the slope is that derivative with c substituted. So when I plug this c into the derivative function, negative sine c, the sine and the inverse sine cancel out, and I'm left with just -2 over pi. So taking this c and plugging it into the derivative function right here, again, the sine and the inverse sine cancel out, and I'm left with -2 over pi. So that's the slope. The c value is inverse sine of 2 over pi, and then I'm going to take the y value, f of c, move it to the right side, and I would just take my calculator and say, take that c value and plug it into y1. So that's the equation of the tangent line. The secant line is even easier because one of the 2 points that I'm connecting is on the y-axis. I can just use slope-intercept form. The slope is -2 over pi, which we had here, and then the y-intercept is 3. So the secant line is just y3 is -2 over pi x plus 3. If you type those two in your calculator along with y1, you should see the cosine curve, you should see the tangent line and the secant line all looking very nice.